Hello, everyone, and welcome to KITE Research Rounds. It's my great pleasure to introduce our speaker today, who is Professor Diego Guarín. Dr. Guarín is an assistant professor in the Applied Physiology and Kinesiology Department at the University of Florida, where he's been since August 2022. Before joining the University of Florida, Dr. Guarín was an assistant professor at the Florida Institute of Technology from 2020 till 2022. Dr. Guarín completed his master's and doctoral degrees at McGill University, and subsequently he was a postdoctoral fellow first at the Harvard Medical School and then later with us at the KITE Research Institute, Toronto Rehab, working with Professor Yana Yunusova and myself. His research focuses on understanding how movement is affected by neurodegenerative diseases and developing novel techniques to measure movement, assess disease severity, and evaluate the effectiveness of therapies. Dr. Guarín's research lives in the intersection between neuroscience, machine learning, and signal processing. His overall research goal is to improve current clinical practices and facilitate remote early assessment of neurological conditions that affect movement. He's published more than 20 papers in international journals, and his research has been supported by different multiple founding institutes and agencies, including the NIH, Michael J. Fox Foundation, the Vector Institute for Artificial Intelligence, NSERC, and the Colombian Department of Science, Technology, and Innovation. Please join me in a welcome round of applause. I'm going to pass on the mic to Diego.
Right. Thank you so much, Mark. It's really a pleasure to be here and be back to Toronto Rehab Institute virtually. Hopefully, I will go back soon to visit you guys. And thank you, everyone, for being here and listen to my talk about early motor deficits in Parkinson's disease and how we can use AI to unmask these deficits. So let me start discussing a little bit about Parkinson's disease. It's not a really common disease, so not everyone knows about it. Parkinson's disease is a neurodegenerative disorder that affects more than 10 million people worldwide. So it's still considered a rare disease, but the number of people that suffer it is quite large. So the number of people that suffer is growing significantly because the biggest risk factor of PD is age. Usually you see Parkinson's disease at age 65 or more. And the more elderly population, the more Parkinson's disease we are seeing. So this is a disease that is actually the second fastest growing neurological disorder, and soon is going to stop being a rare disease. So Parkinson's disease includes many symptoms, including motor and non-motor symptoms. In particular, we're going to discuss the motor symptoms of Parkinson's disease, which are bradykinesia, tremor, rigidity, and postural instability. And we're going to focus mostly on the bradykinesia piece, and I'm going to tell you why in a moment. So Parkinson's disease was originally described more than 200 years ago by Dr. James Parkinson, and he called it the shaking palsy. The way that he described it in his manuscript was that people with this disease had a sunken posture, had tremors, that's what the shaking palsy, and had slow movement. So people that move very slowly and had this postural particular position that you can see here. Of course, our knowledge of the disease has progressed widely in the last 200 years. And we now know that Parkinson's disease is produced by the death of dopamine-producing neurons in the substantia nigra. The substantia nigra is a small part of your brain, part of the basal ganglia, that is involved in many functions of the brain. And those functions include movement initialization and movement control. There are other different functions that this part of the brain works. It's basically an integration center. And so as you can see here in a healthy person, you have the dark mean many neurons occupying this area. And as Parkinson's disease progresses, these neurons are going to die. And as you see here in this person with Parkinson's disease, those neurons are basically non-existent anymore. This is also a natural part of aging. So as we age, we all have death of the dopamine-producing neurons in this region. But in Parkinson's disease, the death is exaggerated, so accelerates and is much, much faster. And as you can imagine, this death of neurons doesn't occur overnight. Parkinson's disease is actually a very long, takes many, many years for going from this condition when you're healthy to this condition where you are in advanced Parkinson's disease. And we now understand, and this is a very beautiful diagram that I found, that Parkinson's disease starts at least 2 decades before you can actually diagnose it. But before the diagnosis occur, you have symptoms that are non-motor symptoms. For instance, you have problems sleeping, you have depression, you have cognitive impairment, starting having cognitive impairment. You might have constipation. And all those symptoms are produced by the death of these neurons in this part of the brain. But those are not specific symptoms. So many diseases have similar symptoms. So you cannot have a diagnosis based on those symptoms. When the damage is large enough, you start having motor symptoms, which are tremor, relative bradykinesia, as we discussed. And that is where clinicians can actually do a diagnosis because those symptoms are more specific to Parkinson's disease. So clinician will take a look at your past history, will see if you have any of these pre-diagnosis symptoms. And now if you combine that with the presence of motor symptoms, they can reach a diagnosis. Very interesting that the patient that Dr. Parkinson described, we will see it around here. And as you can see, in the last 200 years, we have been able to make a diagnosis much, much earlier. So we are now here where we have started these motor symptoms. So we can identify who has Parkinson's disease much earlier. So the goal of my research and the goal of many other researchers around the world is to improve early diagnosis in Parkinson's disease. And why do we want to improve early diagnosis? Well, as you can imagine, in this region, so before current diagnosis, you still don't have motor symptoms, so the damage of your neurons is still not large enough. So if you can identify the disease here, you have the ability to apply neuroprotective therapies to prevent more motor neurons from dying. So you will be able to basically prevent the occurrence of motor symptoms or delay the occurrence of motor symptoms in patients with Parkinson's disease. So if you could start a therapy 5 years before the clinical motor symptoms occur and delay the occurrence of the motor symptoms for 1, 2, 3, 4, 5 years, that would be a really great success and something that researchers around the world are looking for. So when I talk about this, people ask me, okay, so what can a person do if they say, okay, you're going to develop motor symptoms in 5 years or in 3 years? Well, I'm not a clinician. I'm not involved in drug development. I'm more movement sciences. From the movement sciences world, we know, for instance, that exercise seems to have neuroprotective effects in Parkinson's disease. So animal models that do exercise early on the disease progression have better outcomes. This can be proven in animal models. And some research in humans have also shown evidence that if you do exercise early in the disease progression, you might have better clinical outcomes. There was actually a recent study that involved more than 10,000 people, and these people were followed for many years since diagnosis and as the disease progressed. And one of the major outcomes of this study was to identify that people that did exercise and not simply walking, this was actually a strenuous activity during the week, at least 2.5 hours a week, had better clinical outcomes, but they had better clinical outcomes if they did it earlier on the disease progression. So this shows some evidence that indeed exercise might have some neuroprotective effects in humans as it does in animals. So imagine if you start doing exercise way, way before you being diagnosed with Parkinson's disease, you might think that you're probably going to have, you're going to enhance the benefits of this disease because you have more neurons to protect. So that's basically our goal. In addition to this, I have been doing a little bit of research, and the number of clinical trials on Parkinson's disease has been growing steadily for the last 20 years. So basically, pharmaceutical companies are really interested in developing new therapies for Parkinson's disease, and many of those therapies have the potential to be neuroprotective. So there is hope that in the future we're going to have actual neuroprotective medicines that are going to help these patients. All right, so we have saying that it's important to do early diagnosis, but how can we actually do early diagnosis? That's the big question. In actually some researchers from Montreal, this is one study of May and Montreal in 2012. They took people that had the early signs of Parkinson's disease, so basically the pre-diagnosis symptoms that I discussed before, and they followed them for many years until they developed Parkinson's disease, also until a clinician was able to diagnose Parkinson's disease in these subjects. And they found that bradykinesia, basically a slowness of movement, started to appear or was evident for the clinicians at least 4 to 5 years before reaching clinical diagnosis. The other symptoms were not as evident before diagnosis, but bradykinesia was. So basically what we are looking here is that if we could identify the presence of bradykinesia in a subject, and we combine that with other preclinical symptoms, we have good evidence that this person is likely to develop Parkinson's disease, so we could start doing these neuroprotective therapies. And how do we measure bradykinesia? Well, as I say, bradykinesia is a slowness of movement. It's also accompanied by, sometimes accompanied by slow movement amplitude. Low movement amplitude is also accompanied by halts or freezing in the movement, and also accompanied by another more feature called sequence effect. So bradykinesia is so important in Parkinson's disease that clinicians have developed standardized methods to measure it. And they created a set of more tests that they can apply to the subject. And these more tests will allow the clinician to quantify the degree of bradykinesia in the different limbs. And here are the tests that the clinicians have developed. This has been used for many years. They have been improved, and they have had several iterations. And basically, every neurologist in movement disorder knows about this test, know how to use them. And they have actually a script, and here's the script, where they have a way to describe how to do the test to the patient. The patient will do the test in front of the clinician. And then using this description, they can apply a score to the test, going from 0, meaning that the person is moving normally, to 4, meaning that they have a severe degree of bradykinesia, and they have the 0, 1, 2, 3, and 4 scores. Clearly, it's not as easy as it seems. You really need quite a bit of training. And if you don't have enough training, you might start making mistakes and combining these different scores, 0 to 1 or 1 to 2. But clinicians that are trained on movement disorders, have quite a bit of experience in this, can apply this test very successfully. And you can even get trained if you go to the Movement Disorder Society. You can get trained to apply this test and get certified. And then you start gaining experience of this. It's quite an interesting process. Also, in the last few years, especially since the pandemic, a lot of clinicians started to apply this test using telehealth. So basically, patients no longer need to go to the clinic. They can have a telehealth appointment. The clinician will ask the patient to do the movement of this more test, and then the clinician will be able to do a scoring. There is several research showing that the telehealth and the clinical assessment, at least for bradykinesia, basically provide exactly the same score. So to assess bradykinesia, we can do it using telehealth. So the solution is clear, right? So what we need is that every person that is around 50 years old should have an appointment with a neurologist specialized in movement disorders. It can be a virtual appointment, so they can track if they have bradykinesia. And if they do, then this person should start doing different therapies to start the neuroprotective effects that these therapies might have. So in case you didn't notice, this was a joke, because there is a huge problem with neurologists, and is that there is no neurologist enough to cover even the number of existing patients. This has been known for at least the last 10 years, and there is simply not enough neurologists available to cover the demand of patients needing neurological services. The shortage is general, so there is no movement disorders, a subspecialty of neurology, and we have exactly the same situation. There is simply not enough neurologists specialized in movement disorders to cover the needs of all the Parkinson's disease patients. So this was a highlight for the 2019 neurology conference, and this is a recent article in the media saying exactly the same. So basically the doctors know, and now the patients also know that there's simply no enough neurologists to cover the need for current neurological patients. And because a lot of these diseases grow with age, and our population is quickly aging, so this shortage is going to get worse as time progresses because more people are going to be needed, and there is no way to train neurologists faster. These two pieces of media were for US, but Canada has exactly the same problem. So this is from the government of Canada, showing that the neurologists, there's a shortage of neurologists. If you go to UK, they have the same problem. If you go to France, they have the same problem. If you go to Spain, they have the same problem. So basically all the countries that have an aging population, mostly Europe and North America, and also Asia, they all have a shortage of neurologists. There's simply not enough to cover the need. So no, the solution that I mentioned is not possible. We all can't have our own personal neurologist to track bradykinesia. So we, as technologists, we need to come out with a solution. That's what we do, right? Come out with solutions using technology to help solving these problems. The clear solution, and probably the most that people immediately think about, is wearable devices. And these are basically smartwatches or wearable devices. Smartwatches are the most common one. They are user-friendly, so you just buy the watch and wear it and you don't have to do much about it. They allow for continuous data collection. And very interesting, you have the ability to collect multiple data sources. So Parkinson's is movement, but Parkinson also involves autonomic disorders. So you could have heart rate and see how it changes. You can also have respiration. And as you go with fancier devices, you could have additional sensors that in the device to track multimodal data. So they might be able to provide additional views of the patient and the patient's health. And also they're relatively inexpensive. So you could buy a smartwatch for a cheap one for $100. If you go to a fancier one, it's probably $200, which is relatively cheap. Wearable devices do have some problems. And in Parkinson's disease especially, we know that many of the patients with Parkinson's disease suffer more symptoms unilaterally at the beginning of the disease. So basically one side will have more symptoms than the other. And so if you wear the watch in the side, and you don't realize that your one side is getting worse because your brain is trying to compensate. So you don't really know which side to put the watch. So if you're wearing your watch in your left hand and your right side is getting worse, then your watch won't be able to capture those changes, right? So you're basically not being able to capture just because you don't wear the watch in the right side. So to track the device, track the symptoms, you will need to wear multiple devices as the person here. Also, some people start having symptoms in their lower limbs rather than the upper limbs. And those, of course, won't be able to capture if you're only wearing a smartwatch. Also, we know how bradykinesia looks like in terms of the exams that the clinicians perform. They have been tested, retested, and we have a really good understanding of how bradykinesia looks like in terms of those examinations. We don't know how bradykinesia looks like in terms of data provided by a smartwatch. There's not enough data and not enough knowledge. So we'll need to collect a lot of data to be able to make a link between the data provided by those smartwatches and the data and bradykinesia and the different degrees of severity of bradykinesia. Further, only around 10% of people aged 60 plus owns a smartwatch. So even though they're inexpensive, you do need to have this person buying an extra device, which not everyone has the ability to do it. And lastly, people need to remember to wear the watch. So if you're like me, I have a watch, but I wear it only when I'm doing exercise. I just forget to wear it every day. And there has been reports that people that are involved in the studies of wearing the smartwatches, they wear it during the study, and then after 3 months, they are asked again if they're using the watch. Most people say no. It's just a nuances that they don't want to use it. Because the watch doesn't really tell the person anything. It's just sending data blindly to the data center, so the person doesn't really understand what the watch is doing, so they're not motivated to use it. So what other alternative? Another thing that came out when I was reviewing this is that the wearable watches or wearable devices field is really saturated. There are many companies already trying to build apps or solutions using smartwatches. So I believe that definitely there's going to be a solution using smartwatches to track people with Parkinson's disease. But there's still some gaps that we need to fill. And I believe that the best way to address these needs that I described here is using a device that most of you already own, and probably a lot of you already have in your hands, and it's a smartphone. So there is a lot of data showing that most of us own smartphones. And I'm not talking about just to make phone calls. I'm talking about actual phones with cameras and apps and all that stuff. So in the US, at least people 65 plus, more than 60% of own a smartphone, and this was data for 21, and of course this number is growing. So I believe that around 70 to 80% of people 60 years plus owns a smartphone, so they already own it. They don't need to buy a new device. And data shows that at least, even if you don't own a smartphone, someone in your household owns a smartphone. So at least 80% of households in US and Canada have a smartphone in the house. So it's basically becoming a common household item. So why don't use the smartphone directly to collect this data? And the proposal that we have is to use videos collected with a smartphone to assess bradykinesia. And the beauty of this is that we can use exactly the same video, the same tasks that the clinicians are doing. So finger tapping, hand movement, all the tasks that the clinicians are doing, just record it through a video and then process those tasks and provide exactly the same analysis that the clinician is doing at the clinic. So we will basically automatize the process of assessment of bradykinesia in the same way that the clinicians are doing. So we are skipping the need to do our own analysis and to understand how the data relates to the disease, because we are doing exactly the same tasks that the clinicians are doing. So this is kind of the dream. So basically a person sits down in front of their iPhones or their smartphones. They record the different tasks that are involved in bradykinesia. Then we apply AI magic. And then the AI magic will tell us, okay, this is the disease severity for this particular task. And then this information can be sent to the clinician or can be stored for the patient. The patient will be able to see, okay, so it seems like they can record this data for a year, and you can say, okay, it seems like my scores are stable, there's no change, or it seems that my scores are changing and getting worse with time, so there is something that needs to be done. So then there is a motivation for a neurologist to see this person, and they can make an appointment. And so we don't need to have everyone involved in that. All right, so let me tell you a little bit about the AI magic. That is basically the part where we have been working in the last few years. And so the first thing that we need to do is how do we actually estimate movement from videos, because all this is about movement. So thankfully, that problem has been already solved for us, mostly solved. And it's a machine learning method called pose estimation, where basically these pose estimations are AI algorithms that you can apply to images to estimate the pose of a person. And here's an example of different poses and the output of those algorithms, so the location of different joints. And then you can make skeletons of people. And then a video is just a collection of frames that you can track how those different points in the video move along the video and basically estimate the overall movement of the person. So this sounds like a little bit of black magic for some people. Of course, most people are not familiar with this. But if you have used any of those very famous apps like Instagram or Snapchat and use any of the filters that the app includes, then you have already interacted with these algorithms. So basically all these apps, they use the same technology. For instance, this is only for the face, but it's exactly the same technology. There is a model behind it that identifies the different components of the face. And then these apps add these colorful things to the face based on the location of different parts of the face. And if you have ever used it, you know, they track how you move, they can identify your mouth movement and everything. We are basically using the same technology, just applied to the body. And funny enough, these companies, even though they are not involved in any medical related field, they have moved the field quite enough and make these technologies very accurate. They have this specific application, which is entertainment, and we just exploiting it to use a different application. But this solution already exists. It's very accurate algorithms. They're really fast, so you can see it running in a cell phone. So we are exploiting that technology for different use. All right, so what is that we do? So we take our frames of a video. So this is a video, an image of someone doing, say, a finger tapping task. Then we apply deep neural network processing to the frame, and then we obtain the position of different landmarks in the person, which are pre-established. And then we just do the same for all the frames in the video, and we track how these different landmarks move along the video. This is an example, for instance, for hand tracking. So here, this is the original video frame. We applied our algorithms. The algorithm provides the location of these landmarks. And then as we do it through all the videos, we then process and identify the distance, for instance, between the tip of the finger and the thumb fingers, the tip on the index and the thumb fingers. And then we are able to track how that distance changes a long time as the person performs the finger tapping test. In our particular way to process this data, we then use these signals to extract features of movement, like the movement amplitude, movement speed, and other things that we know clinicians are looking for when they visualize people doing this test. So we are trying to have the eyes of the clinician just using a computer vision model. We can do the same for gait. So this is an example of a frame of a subject walking, the result or machine learning algorithm to post-estimation. And then we process all the videos the frames in the video, and we can extract, for instance, gait events, left heel strike, right to off, and so on. And then with that information, we can compute features like gait speed, cadence, and other important features for gait. All right, so we have done a couple of studies using this technology, trying to see if we can actually use it for early detection of bradykinesia. The first question that we had is, can we actually embed this technology into a telehealth appointment? So doctors are really doing telehealth, as I described earlier, and patients are doing this test during the telehealth appointment. Could we just embed these algorithms in those platforms? So that would be a really nice solution. This was actually work done by my student, Gabriela. And we did kind of a funny experiment where we have a subject doing a telehealth appointment. It's a computer. And the subject was asked to perform the different tests of bradykinesia. And at the same time, we were recording the subject with a camera. So this is a standalone camera. And so we have two videos. We have one video that it was recorded by the clinician on the other side of the telehealth call, which we call a streaming recording. And then we have another video, which is the one provided by this camera, that is basically a device recording. So these are samples of that data. So this is a person doing the finger tap. So again, the two videos are basically seeing the same. We put them such a way that we can see the same view. We can have the same view. And as you can see, the on-device is more sharper than the one we have on streaming. The streaming depends on the internet connections. Basically, that's the biggest factor, internet connectivity. And so the streaming device adjusts its sampling rate, adjusts a lot of factors depending on the internet connectivity. We make sure we have good internet connectivity for this, but that is something that you cannot really control. So as you can see, the person is moving the finger, so it blurred out completely the finger. It didn't capture the data. whereas on device recording, it did capture the data. We also tested many models for post-estimation. So we basically went ahead and searched for different available post-estimation models. We collected 7. We implement them. We were able to use them. This is the data from those 7 models, and we tested them all. So we basically passed them all our data through all the different models. We also did another thing where Gabriela did another thing, is that she manually annotated the tip of the index and the thumb finger in each one of the video frames. So we have true data of how the distance of these 2 fingers changed during the execution of this task. We have 10 subjects, so she basically spent a lot of time annotating all these videos. And this is some of the data from one subject. So this is some subjects basically did very fast tapping, so they did like this. Some subjects did slower tapping. The instructions say they should do fast and large tapping, but you cannot control the way each person moves. And we have a wide variety of ages. We have people from 20 to people from 60 years old. So we saw a lot of variability in our data. So for streaming, the blue is the manual annotations performed by Gabriela, and the orange is the best model that we tested. The green is the worst model that we tested. So for streaming, when the movements were slow, so you see here, they basically are doing 2 taps per second, so they're slowly tapping. The best model was really close in results to the manual annotation. The worst model was really bad for this. So basically the worst model didn't work, but the best model provided quite a good result. However, when the movement was fast, so basically this person was tapping 6-7 times per second, so they were tapping really fast. None of the models provide really good accuracy for the streaming results. Then when we go to the on-device recordings, both the best model worked well for slow and fast movements, and the bad model worked bad for both the slow and fast movements. So basically what we discover is that tracking movement from a streaming recording is really unreliable, especially if you are doing fast movements. So sadly, we cannot apply this tracking technology to the telehealth recordings. We will need to have our own on-device recordings for this to work. But we also found that some open source post-estimation models that are already available out there do a really good job at tracking movement, especially for on-device recording, even if you're moving fast or if you're moving slow. So we're very happy that we can reliably estimate movement amplitude, movement speed, frequency, and rhythm from videos using the best performing model. And so basically that's the model that we're still using nowadays. The model has been actually improved. It's by Google, a small company that you probably heard about. And the model has been improved in the last few years. So we just keep using that model because it keeps getting better and better. And Gabriela published a paper with these results. So now, we have these videos, we have this data analysis from the videos, we can get these features from the videos. But clinicians are usually used to score these videos on a 0 to 4 scale. So if you want to tell the clinician, hey, the machine can help you to assess patient's movement and provide and assess the severity of the disease, you will need to have the 0 to 4 scale that the clinicians are used to. You might add additional results, but you do need to have that 0 to 4 scale. So it's basically a part of the problem. You need to add it to solve that problem first before being able to move forward to other things. At least that's the way we see it, and at least that's the way that clinicians have told us that we should move forward with this. So we are not the first ones to do video assessments of bradykinesia. There are a couple of studies already available, and they have been published more and more every day. So people have already done this. People have tried to do prediction of the 0 to 4 scale using video-based measurements. And this is a result from a paper. This is a paper published in 2024. And what most people do is that they take all the features and they basically create a multi-class classification problem. And so they want to train this model to identify between the 0, 1, 2, 3, or 4 score based on all the features provided by their video-based processing system. And as you can see here, this is basically the score provided by the clinician, and this is the score provided by the model for the study. It's not very successful. I mean, you have probably 60% accuracy or 50% accuracy, which is not great for machine learning models. Well, looking at this data and knowing a little bit about the disease, this process of doing multi-class classification doesn't really make sense, because at the beginning of the disease, you have some symptoms, then those symptoms are going to change as the disease progresses. At the middle of the disease, you have other symptoms, and then those are going to progress more, and then you're going to have other symptoms. Some things change faster than others, like especially you start having movement issues with speed, then you start having tremor. And so it doesn't really make sense to say, I'm going to have a model, a big model that is going to be able to separate all the different disease severities based on exactly the same movement features. And as you can see here, for instance, 0 to 1, the amplitude is exactly the same in movement, 0 to 1 score. But when you go to a score 2, the amplitude now is very small. So amplitude shouldn't be used to separate the score 0 to score 1. Amplitude should be used to separate score 1 to score 2, right? And there's a decrease in amplitude, but not here. So we thought about this, we discussed with some clinicians, and we came out with an alternative, and it's basically use tiers instead of using a single model. So we propose a model or a group of models that have different models for different severities. So a first model will be able to separate the people without Parkinson's disease from people with Parkinson's. A second model will separate the lowest score with the highest score. And a third model will be able to separate the scoring, the people with the worst condition. The interesting part of this model is that we allow our algorithms to identify the more important features by themselves. So we basically ask the algorithms, okay, what are the most important features to separate these two groups? Here we ask, what are the most important features to separate these two groups, and so on. And so we call this tiered prediction. And so we wanted to see if this kind of model worked. So we did a little experiment. So we collected some data. We collected it from 90 subjects with 66 with PD and the rest with healthy controls. The PDs had a variety of disease severity. We apply our pipeline to detect quantified movement from videos. And we trained two different classification algorithms. We trained the multi-class classification, which is the classical that people use, and we trained the tiered classification algorithm, which is the one that we were proposing. And here are the results. So the multi-class, we have, as expected, we didn't have anyone with score of 4, but we did have people with score 0s, 1, 2, and 3. And as we expected, the accuracy is low. It's around 55, 60% overall, similar to what other people have reported. So this is what you see typically in PD papers reporting classification accuracy, which is not great. Applying our process, the accuracy jumped quite substantially. So for score 0, we got 85%, score 1, 100%, score 2, 80. So it's a rare big improvement in classification accuracy. More interesting is that we asked our models what features are important to you. And we found that the tier 1 model, all the features were related to speed and timing, nothing related to amplitude or variability of movement. So basically at that stage of the disease, there is no change in speed and amplitude or variability is mostly related to speed, which is bradykinesia, which makes sense. Tier 2 model involved many different features. So that was the model that needed most things to make separation between the classes. And the tier 3 model was only focused on variability. So at that stage, you have a lot of tremors. So movement variability plays a big factor. We actually published this recently in a IEEE paper. So if you're interested, you can go ahead and check the results. So we really hope people are going to adapt this model in the future because this is a very interesting topic. So a lot of people are working on this. So we hope that they adapt this kind of model. Now, going back to the question that we started with. So can we actually detect bradykinesia early using videos? So this is, of course, the burning question that I had in my research. So we were able to do a little experiment. These are basically unpublished results, but they're already been submitted. So hopefully the readers will like them. And we collect data from controls, people with RBD. So this is basically one of the symptoms that are related to Parkinson's disease, but they still cannot be diagnosed with Parkinson's disease. So a lot of people with RBD, which is a sleep behavior disorder, will develop Parkinson's, but not necessarily will develop. Some of them will. And with person with Parkinson's disease, we focus exclusively in the finger tapping task, and we identify people that will have a 0 score in the finger tapping task. So basically, you record someone, and if the clinician gives a score of 0 for that test, we then kept that video. So all the videos that we analyze in this paper have a clinical score of 0. You might ask, okay, so how is that a person with Parkinson's disease have a clinical score of 0 for the finger tapping test? It's really interesting, actually. So these are people very early on the disease, so 1-2 years post-diagnosis. And when you start doing levodopa replacement therapy, which is the therapy that they use in Parkinson's, people with Parkinson's tends to get better in their more symptoms for a few years, thanks to the levodopa infusion, but then they start to get worse. So the levodopa doesn't delay the disease progression, but it's kind of an effect that occurs. So the first 2-3 years, they get better, and then they start to get worse. So we basically cut people in that get better stage very early in the disease progression. So they got better. So they basically have no more symptoms that the clinician could see. So if you take all those videos that we gather and you give those videos to a clinician, the clinician will say, for all those videos, none of this person has Parkinson's, based only on that video. Of course, if you combine then the history of the patient and other examinations, then in that case, you will be able to get to the diagnosis, but only on that video, the clinician will say there is no Parkinson's here. So we apply our processing, and we were really happy to see that even in those videos, there is a significant difference in the movement amplitude for Parkinson's disease, so lower movement amplitude, and movement speed, so lower movement speed. So even those people that the clinician wasn't able to see if they had bradykinesia, or video processing algorithm was able to see that there is bradykinesia occurring in those patients. So we were able to detect bradykinesia earlier than a clinician would be able to see, based only on a single video, which is very interesting. We then train classification algorithms to separate the groups. So again, based only on the videos and a clinical observation, you won't be able to separate any of the classes. But based on our processing algorithm, we did separate the classes. So we got accuracy of 88% separating healthy controls from Parkinson's disease patients. And interesting, we were able to detect most of the Parkinson's disease patients. Some of the PD, we got confused with Parkinson's, and then we went and looked into this PD, some healthy controls were confused with Parkinson's, and then we looked into these healthy controls, and they were older, and they had some signs of bradykinesia, which is also occurring with age. These results are also very interesting, but they're basically part of the discussion of this paper, hopefully, but they're not really important here. But yeah, so we basically identified almost all the PD subjects using our video processing algorithm. So it's a very exciting result that we were really happy to see, and hopefully we can reproduce it with larger population. So basically, we found that video-based analysis is much more sensitive than a training clinician at detecting those subtle changes in movement amplitude and speed during the finger tapping task. Video assessment basically offers a really low cost and scalable solution to track progression of bradykinesia, because we now can see objectively how the bradykinesia is going to progress in those subjects with Parkinson's disease over time. All right. So when we talk with our collaborators, they say, yeah, that's great, that's fantastic, but we cannot give you our video data because it includes the patient's face. So that's it. Your work stops there. No one is, or most clinicians won't be able to develop their own video processing algorithms. So there is no way to apply these techniques and to take advantage of what you have shown with our own data. So we took that at heart, and we have been working really hard in the last few years. And this is work basically for most people in my lab. some collaborators from computer science and two students in my lab, Carolina and Gabriela, have been heavily involved in this. And we developed a software to apply basically the same process that I described. The software is able to apply the process for most of the bradykinesia related tasks of the MDS-UPDRS. And in this software, you basically upload your own video, you select the task that the person is performing. The video is then processed using our algorithms, the same one that we have used in our papers, and then it provides movement characteristics of the video. So it provides both the movement data. So for instance, for the finger tapping, in here you're gonna see that provides this it shows the distance between the index and the thumb fingers, and also provides values related to these feature characteristics. The software is currently available. If you go to visionmd.ai, you can download the software. There's a version for macOS. There's no version for Windows. I'm still working on it, but there is also the code there that you can download and execute. And the code is available. You can modify it if you want to. You can adjust it to fit your own needs. There's actually some collaborators that have made some changes to the software to fit their needs. And we are trying to make it such that it's a modular software so that you can plug and play pieces that you need. We're trying to get NIH to give us some money to be able to make this software more accessible and so that everyone can use it. And again, another important thing is that this software runs locally. So there is no data sent to internet or anywhere. If you have a GPU, it's really fast. If you don't have a GPU, it's a little bit slower, but it's still relatively fast. So it takes probably 1 minute to process each one of the tasks. So it's not really a sluggish software. And we are improving it. We're constantly improving it. So we're very proud of this product. We actually submitted a paper showing it, and we hope it will be published in the next month or so. All right. One of our collaborators from Germany, he had around 500 videos of people with Parkinson's disease doing all these different tasks. And in his test, he's doing a levodopa therapy or the levodopa test. So basically, you come to the clinic with a levodopa, and then you take a large doses of levodopa, and then they do the test before taking the dose and after taking the dose. And he was able to objectively characterize how this levodopa therapy affects movement. But it's very interesting because he can see all the different realms of movement using VisionMD. So he can see how all these different characteristics are affected by levodopa. And he found that levodopa is mostly a velocity affecting therapy. So all things related to velocity are affected or improved by levodopa. But things related to, for instance, variability of the movement are actually decreased by levodopa. So if you want to, for instance, if you find another therapy that improves variability, then you could combine levodopa with that therapy and apply this same approach to see how those two therapies affect the different elements of the disease. So we believe that this is going to change the way that we look at the disease, because we now have very specific characteristics of the movement and how they're actually affected by the different therapies. So we hope that this is how clinicians are going to start analyzing the effects of therapies in the future. And this is a paper in preparation. So these are unpublished results, and it's coming out from our collaborators in Germany. All right, so what is that we are working on for the future, especially in the short term? So we would really like to move to do gait assessment, and not any video-based gait assessments, and not any gait assessment. We want to do frontal view gait assessment so that people can actually do this at home. So apply gait assessment at home. Most gait assessments are now from lateral view videos. So you need a large space to do gait assessment from videos, but we want to focus on frontal view gait assessment. This is work that my student Yu is working on, and we hope to have a product really soon. We're also developing a large normative database. So we're basically collecting people 65 year plus that are healthy, because we want to create a large database of videos of how healthy looks like in videos. so that when you bring a patient, you can have a point of comparison. Because there is a lot of information about the test as seen from the clinician. There is not a lot of information about how the test look from a video perspective. And so we want to do this kind of data. This is from Jackson, one of our students in my lab. And also Gabriella's PhD work is going to be focused on the correlation between brain activity and kinematics in Parkinson's disease. And so we're basically synchronizing brain activity recordings in persons that have a deep brain stimulation, and they have a sensor in the deep brain stimulator. So we are going to record brain activity from within the brain. And then we're synchronizing that with kinematics data that we record from video, so that we can understand how brain activity in Parkinson's disease is reflected in the different components of the disease, such as bradykinesia and so on. And this is Gabriella's PhD work. So this is for short term, so projects in the next 1-2 years. For the long term, what my lab really wants is to bring this solution to the public. We want everyone to be able to do self-assessments at home and to fulfill the desire that I had at the beginning, that I discussed at the beginning, where you basically are able to track how bradykinesia is progressing. And if you have symptoms of bradykinesia, then you will be able to contact a clinician and tell them, hey, it seems that I have bradykinesia, so let's do an additional test to see if I'm a good patient for these neuroprotective therapies. We actually, our dream here is to make an app that everyone can use. With the app, it's going to allow you to record the data, process the data, and then provide a score of bradykinesia. And so we're working on it. I'm working this with a very talented student from my lab, Nishan. And we made an app. The app is currently available, and you can download it, record data, video data. The data will be uploaded to our server and then processed using the different technologies that I described before. And then you will have a score, bradykinesia score, that you are able to track over time. So we basically want all people to be able to track their bradykinesia at home. This is the long term from our lab. There's a lot of hurdles to do this kind of work. So we are considering what is the best next step. All right, that's it for me. Thank you very much for your time. I want to thank for all the people in my lab that has worked on the different projects. I have many collaborators in EF, my chair, and people from the Pixel Institute has been monumental to get this data and to understand how to process this data. So everything is guided by their knowledge, because they're the ones that interact with the patients. And also people from outside of EF that have been really helpful and have shown interest in this work. And also to everyone that has given me money so we can do our work. Thank you all for listening. And if you have any questions, I'm open to it.
Wonderful. Thank you, Diego. Let's thank our speaker in a virtual round of applause. Dr. Guarín has mentioned to me at the beginning that he needs to leave around 1 o'clock. So we still have a few minutes for any questions that people in the audience might have. If you have a question, you can raise your hand or type it in the Q&A box and we'll answer it. And while you get started on that, maybe I can start with a question. Have you considered or have you done or considered doing in the future to assess also dyskinesia or levodopa-induced dyskinesia and differentiating between that and Parkinson's?
Yeah, so basically with this technology, we can analyze multiple factors. I've been focused mostly on bradykinesia, thinking about the early part of the disease, because I do believe that early diagnosis is really important. But we can analyze all the different components. We just need to sit down with a clinician and figure out what is that they're looking for when they analyze the different parts. For instance, right now we are working on tremor, which is also a big part of Parkinson's. It typically appears a little bit later in the disease, not just right in diagnosis. So we are developing different algorithms to be able to track tremor Parkinson's. So yeah, it is I think we have the opportunity to track all the different components of the movement with this technology.
Yeah, we should collaborate more. We're working on
Definitely,
similar
yeah.
things, and we should plan that more formally and collaborate more. People in the
Yeah,
audience,
100%.
yeah. Are there any questions? Oh, there's one new question. Do you want me to read it out loud, or you can read it?
Yeah, that would be
Okay.
better. Yeah.
So this question is from Derek Lim, Rui Chuan, and they're saying, awesome talk, Dr. Diego. Do you anticipate any obstacles when moving into video diagnosis using gait data, while having a clinician in a video to support the participant cause problems?
So this is a very interesting question. So we are actually working right now with another team that works with kids, and all the videos that they have sent us have a clinician in there because the kid might fall. So they are continuously working with the kid. So there are a lot of improvements of video tracking. So basically identify who the person is in the video and then track how the person moves through video. So we have been exploring that technology and it works relatively well, but definitely needs to be improved. So I believe that there needs to be an initial step to identify who is that person that you actually want to analyze. And once you have that, then you can do the processing. So that might hurt the automatic processing, but it's a very simple step where you click on who is the person of interest, and then you track that person through a video. So yeah, it's not a great solution, but at least there's a solution to that problem.
Thank you. We're approaching 1 o'clock. We may have time for maybe one quick question, because it's just turned 1 o'clock. If not, we can thank our speaker. Thank you, Diego, for a wonderful talk, and look forward to collaborating more.
Thank you so much. Yeah, of course, we are definitely very interested in getting this to other people's hand, and looking forward to chat with you more, especially on the gait, because you guys are the masters, the experts in gait analysis. So hopefully you can learn from you.
All right. Talk soon.
All right. Thank you so much.
Bye.
Have a great day.
Okay, awesome.
Bye.
Thank you, Diego. Let's be in touch. We have quite a few interesting things coming out soon, including one
Great.
on gates that is currently under review on generating synthetic data.
Oh, cool. Yeah, we are going to start collecting gait from people with ear problems. So we're trying to evaluate residual gait impairments after basically people that have inner ear problems. They get to treatment, they solve the inner ear problem. We're trying to see if they have residual gait issues.
Yeah.
So we're trying to find algorithms that can help us to quantify that.
Yeah, we have some code available already, and more coming soon.
All right. So let's get in touch, because we definitely want to use that.
Okay.
All right. Thank you so much. I have to go to the next meeting.
Bye-bye.
Thank you again for inviting me.